Questions. We have one from Yale University, and I'll try to answer it with a slide that I found somewhere in my slideshow. The question is, what's with this flamelet idea anyway? Norbert Peters and Professor Law are really credited for this whole idea, although there's been some other people before them, Clement in France and others, but and Foreman Williams. But this is kind of the picture that has emerged, and that is if you have a thin segment of a turbulent flame. Now we're saying a turbulent flame is consisting of a thin-looking reaction zone. Whether it's premixed or non-premixed, and it's wrinkled and moving in space in an unsteady manner. I do this for premix, but it doesn't matter. If the velocity is 3 meters per second coming this way, tangential to the flame, and 5 meters per second up here, tangential to the flame, we say there's a velocity gradient or it's being strained. And I think you can imagine that velocity field will tend to stretch this rubber band until it gets longer. You'll increase the area, and it might break. It's just like a rubber band, right? But the theory is based on the idea that any constant mean velocity doesn't do anything. So if you had 4 meters per second here, and you had 4 meters per second up here, it wouldn't do anything, because it wouldn't stretch it, it wouldn't shrink it, it wouldn't do anything, because pretty much all the gradients are normal, and if there were no gradients this way, the constant velocity wouldn't do anything. And if you look at your equations for laminar flames, whether they're premixed or non-premixed, if there's no tangential velocity that appears, there's a tangential velocity gradient, dv dx, du dx and dv dy. They're great velocity gradients that are important, but a constant velocity doesn't do anything. So the argument is you can just subtract 4 meters per second from this point and 4 meters per second from this point, and it won't change anything. And so, of course, that will cause this to be 1 meter per second, and this will be 1 meter per second this way. And so this, we argue, is a counterflow geometry, and therefore that this point P here can be represented by a counterflow flow field. In this case, it's premixed. So we would have reactants coming up and going like this, and it would be about 1 meter per second actually at the flame front going out here, and 1 meter per second going this way. And just to do this in the lab, we'd have to have it symmetric, so we would have products going out. And this would be a twin flame. And we argue this is similar to what would happen if these two eddies were approaching the flame and exerting extensive strain. The problems, of course, are that this is a steady counterflow problem with one strain rate, and whereas in a real turbulent flame, you'd have strain rate that's only exerted for a short time and wouldn't be steady. If it was steady, we'd probably rip apart these flames like crazy, but unfortunately, the eddies, or maybe fortunately, the eddies that are around the flame are moving, and they don't just stay in one place, and they go through, and they're gone, and only for a short period of time. And so it isn't just the strain rate that's important, it's the strain rate times the residence time, and that determines how much elongation or contraction you apply to the strain, to the flame. So this is the concept of those lookup tables and those state relations that I'm talking about. They seem to work. Okay, let me go. We were talking about Rob Barlow's data set, which you can download. This is the classic Sandia flame D. It's a very small diameter of 7 millimeters. 50 meters per second is pretty large jet velocity. There's a co-flow around it of hot gases. Now I guess you don't see that much in here. Oh yeah, I'm sorry, this is the co-flow and then the jet is in the middle. Right. Now they argue that the base region is kind of partially premixed because you have this a co-flow, and so it isn't a pure jet diffusion flame. But the problem with the jet diffusion flame is that it would blow out if you wanted to go to high strain rates. So if you go to 50 meters per second, you need to have this pilot flame of hot gases around it that would keep it stable. But it makes it harder to model because you need to model the pilot. Okay. Rob says that his spatial resolution is about 0.75 millimeters. And this is a point measurement, so you imagine a laser being focused down to 0.75 millimeter diameter, and then he looks along the length of it, about 0.75 millimeters. So that's a cube in space of this size. And he does not resolve the Kolmogorov scale. So when he says he makes all these measurements, he's measuring quantities averaged over this size. That's the best you can do. There's always the question of what's happening on smaller scales, but that's what we do, and nobody can do them any better. This is a paper from Barlow, a really nice paper, and again, it just shows the CO is in good agreement with other, let's see, this is a comparison of let's see, getting confused here. I'm not really sure what these solid lines are. They may be, I'll have to go back and look at the paper. Anyway, this is the experimental data, the dots, and he's showing very good profiles and very nice information of all these different species. And it's been carefully duplicated at other places such as Darmstadt so that you know that it's done right. Okay. They report the PDF of the mixture fraction, and you look at these curves, and they look a little bit like that beta function that I put up in a slide. They also measured the nitric oxide. Now, nobody claims to measure, to predict nitric oxide really well, because to get the nitric oxide right, you have to get the temperature right to within maybe 20 Kelvin. And if it's 2,000 Kelvin, that means 1%. And so can we measure things to 1%? Maybe, but that's maybe not. Can we predict the temperature to 1%? No. So, so if you could argue that there's no point in trying to get the nitric oxide to agree with the experiment, but you want it to be in the right ballpark. And a number of models are in the right ballpark. And the other thing is, if you really want to predict the NO, you have to predict the heat losses. So if there's radiation, it better be in there. If there's buoyancy effects, they better be in there. If there's any kind of soot or particulate radiation, that better be in there. So it's hard to get the NO right. And here's another one. Matthias Imme and Heinz Pitch uses a different method, the flamelet progress variable method, which is similar to the flamelet method, but just a little different. And they're off by 40%, but they're quite happy, and I think everybody's quite happy. You could do something to correct the model and make it better, but I don't think there's any point. They did include radiation losses. Now, this slide is up there to show that NOx can be predicted with post-processing. When you think about NOx, it's due to these reactions, and this is part of the Zeldovich mechanism. The O2 gets hot and dissociates and forms O, and then it collides with N2 to form NO, okay? But it does this very slowly, and if we sort of ignore the prompt NOx that's in the reaction zone, this thermal NOx, this Zeldovich NOx, is all produced downstream of the flame. So all you need to know is the temperature field downstream of the flame, as well as the O2 and N2 mass fractions. And so you just imagine a flame here, and then for the next meter above it, there's O2, N2, and high temperatures. I'm ignoring any NOx formation in the flame, and so I'm just in this 1 meter region, how much NOx is produced. Well, I just used my chemistry, and I need to know the temperature, but I don't need to know anything about the other species. Well, OH would be nice, I guess, but in theory, you might know the OH as well everywhere in this big volume. So after you're done with your big computation of whatever you're looking at here, you can do NO computations in a post-processing if you ignore the prompt NOx that's in the reaction zone, in the thin reaction zones. So, but you have to know the temperature very accurately to do this. Right. Here's another example of a more complicated problem that people would like to model. This is Wolfgang Meyer's work at DLR in Stuttgart. And so if you have a fuel coming in, methane, and you have air coming swirling around it, you get this complicated recirculation zone and flow pattern. Adam Steinberg went to Wolfgang's lab for a couple of years and applied these diagnostics, and they ended up with beautiful movies of vortical structures rotating around. He calls this the helical vortex core. This is a vorticity pattern that he obtained with three-dimensional velocity field imaging. It's really quite impressive. And it was also kilohertz, 5 kilohertz. And so, you can see these eddies that are rotating around as this flow is recirculating, and this gives rise to these combustion instabilities. So you hear these loud noises, and ooh, this one came out upside down. Okay, well, everybody look upside down. It doesn't matter, I guess. Again, he's showing these vortex patterns that are rotating. It's a helical, so it's something spinning around, but it's also precessing. So it's like you're spinning a top or a dreidel on a table, and so things are spinning, but then the whole axis of the spinning is also rotating. And he's able to get measurements of all these properties. And in Wolfgang's lab, they can do many of the things they do at Sandia. So, they have many of the species and temperature, OH, all of these things, a huge database. And I point this out because in some cases, people are just doing jets still, and some people are going to much more complicated canonical experiments and trying to get everything measured properly. And DLR is one of the leaders. I don't think anybody has quite modeled that last flow field up to the level of what you'd like, so it's still a challenge. Maybe, maybe some of you can do it. So I'm going to put this slide up, and then I'll take some questions. What's the goal of comparing models to experiments? We need to give some thought to this because you may spend some time in your career doing it. Suppose different models all agree with the measurements. That's fine. There's some, when you model certain terms, you need to put some constants in, and if you try to keep them, the constants constant, then fine. Is there any point in comparing the output without assessing the basic assumptions? Well, we do that all the time, so apparently people do it. But then the question is, in the second point, shouldn't we first compare the output of the models, decide whether they're even working right, and if it's only the ones that work well, then maybe we should look into the details of the assumptions and the terms in the equations, because we can't check out every model. The models agree to some tolerance. Do we need to build a better model for better agreement? Unfortunately, the world is such that, to get funding and to do what you want to do and get theses, you have to sort of do something different than the last person. So there is this pressure to make models fancier and fancier until the so-called large eddy simulations take up more computer time than the actual DNS. And so you say, well, if you're applying models and they take more time to run than the exact DNS, why not just run the DNS? And I think there's some logic to that. We want models to work, but we want models to work quickly if they rely on assumptions, because there's no point in making them too complicated. But there are things we don't have in many models: heat losses, complex chemistry, JP fuels, the variable pressure field. The boundary conditions are usually simplistic. Do we want to identify the best model, or can we live with 20 models? Or do we want to attempt to converge and get 3 or 4 categories of models and live with that? The other thing is, if you don't actually solve the Navier-Stokes equations, but you have some other idea, then how good is that? It may give you the right answers, but if it doesn't solve the equations we think are the basic equations, will that be good in the long run? Or should we attempt to fix whatever isn't realistic in some of these models and make them more realistic? Maybe not, though, because again, if the idea is to use it for engineering purposes, does it really matter if we solve the exact Navier-Stokes equations or if we solve something that's a derivative? In fact, you could probably say that all models take some of the terms in Navier-Stokes and model them with something that isn't real. Is that okay? And well, you have to in order to get a quick solution. But where is modeling going, and are we going to converge at some point, and do we need to converge? So with that, maybe I'll take some questions and see what people think. Yeah. Which one now? This one? Yeah. Mm-hmm. Oh, okay. You wanted to write that down. Yeah. I apologize. This person wanted to just write down I shuffled some of the slides and added more slides, and you're all going to get the final version. Professor Law will give you the final version, but you know, making up this number of slides in a few weeks to the final version is hard. So I think you'll get it on a CD or probably on a flash drive, and I apologize for that. Yes.
You mentioned modeling using I've seen data where these
With the fuel, what?
properties change over time.
Oh, the fuel properties, yes.
Yeah, as well as seasonal.
Oh, yeah. Yeah, the question is that real fuels have properties that change over time. For example, when we run Jet A fuel, we go out to the airport. I usually have to go with my students because otherwise the Homeland Security thinks that we're doing something bad, you know. But we go out to the airport, we just take a big approved container and we fill it up with Jet A, but it's totally different than the Jet A I get in Ohio or in Oklahoma, yes. Now the Air Force has told us they want this because they want real Jet A, and we have to sort of get a spec sheet on what that is. But now other people in our college, Margaret Wooldridge and others, they're creating surrogates, you know, which would be mix a pure kerosene with a little bit of this and a little bit of that, and then that's a pure mixture that you know exactly what fractions of these pure liquids that you got. The trouble is that is never going to be exactly the same as Jet A, and some of the funding agencies want Jet A. GE wanted us to run Jet A. They didn't want a surrogate, they didn't want kerosene, they didn't want, and I know at Stanford they have classified the different JP fuels with lots of numbers behind them. But even then, I imagine each of those groups of JP fuels are a little different. They can have nitrogen in them. They can have lots of other things in them that could be different. I think using surrogate fuels will definitely be the best way for the science community to reproduce data, but funding agencies want the real stuff. I don't know if anybody, some of you work with the auto companies, and you know they want gasoline, right, or diesel fuel, right? Question?
A lot of the models that we are
Yes.
So I'd like to know your comments on the fact that if
Yes. Yeah.
and what models would be better for that?
The question is that that all of these models inherently assume a structure to what happens at the flame surface, either a steady unstrained flamelet or a steady strained flamelet, or the progress variable is a little different. I guess there's three that I mentioned. We don't know exactly what's happening at the flame surface, and so I think you'll see at the symposium in Seoul more and more papers that are attempting to use the diagnostics and DNS to answer your question. You know, what we see in our Bunsen flame is something that looks an awful lot like continuous flamelets, but not real thin. They have very broadened preheat zones. And that's in contradiction to all of these models, really. So, but now you mentioned also then what happens if you start to see distributed or like mild combustion? Yeah, if we start to do these same experiments like in this gas turbine type device, but now if you preheat the reactants to really high temperatures and run JP fuel like you would in a real engine, yes, it'd probably be very different. We might see distributed combustion, but we just don't know the answer to that yet. We sort of have the feeling that if you preheat enough and you recirculate fast enough, you're going to get big globs of things burning, but we don't know what.
These models applicable?
Definitely not. I think these models are going to be applicable to distributed combustion. These models are only valid for layers that could be broad, but still have that layer-like structure where the gradients are large in one direction and not so large in the other direction. So these models are only applicable to thin and broad flamelets, but not distributed. And we don't have a good model for, well, now, Professor Pope, if he was here, he would argue with me. He would say that his model can do distributed because he has a different approach. I didn't mention his model, but he doesn't always make these flamelet approximations. And Professor Menon from Georgia Tech, he has a linear eddy model. He basically simulates turbulence and mixing by a sort of a random process that he has generated in his ideas, and so they don't use the flamelet ideas, but it's not clear whether they're better or not better than the flamelet models. So there are some ideas, but nothing that's been proven. And we can argue about that. Some of you may, if some of you are running Professor Pope's model, you may argue that it does do distributed reactions quite well. But we first have to see them in the laboratory before we can model them, don't we? Okay, another question? Mm-hmm. Mm-hmm. I hope not. Now the question was, if you looked at that picture, I drew a pyrolysis zone followed by a preheat zone, followed by a reaction zone, and that is a cartoon that I drew that I don't think anybody else has ever drawn because we don't know if it's right or not. It's just something I drew for this slide, the question was now, even if you saw something like that in a laminar flame, would it be the same in a turbulent flame? In other words, that analogy that we're drawing between a section of laminar flame, a section of turbulent flame is similar to a counterflow laminar flame. I don't know. We'll have to measure that to see. Most of these things I'm talking about are on the cutting edge and unknown. Another question? Yeah. Yeah, that's a good question. The question is that if you put a lot of turbulence in a flame, our measurements show that we don't have any more increase in area of the wrinkled surface. It just goes up and flattens out. Now, at the last meeting I was asked the same question. Could it be that our diagnostics are not seeing all the surface? It may be that there's more wrinkling than we can see, and that's not the case. We have plenty of resolution, and Other people who do the same, they're also convinced that they have plenty of resolution in their measurement techniques, that the flames that we're looking at just don't wrinkle to the fractal-like small scales. You just, like I said, you can't just take a flame like a piece of paper and crumple it into a ball and have it totally wrinkled like that. I think we've wrinkled it about as much as it can be, and we know that the spatial resolution, the laser sheet, we've reduced it down to just maybe 150 microns thick, and the pixel sizes are 150 microns, and so we don't see any wrinkles that are anywhere near that level. So I mean, some people think, well, there are wrinkles down at the Kolmogorov scale. Well, we just don't see that, and we don't think it's a measurement problem.
I would say that is good.
Mm-hmm.
Basically means that DNS doesn't have to be.
Yeah, that's a really good question. What was brought up was that as you make these measurements and you see that the flame doesn't get wrinkled to the Kolmogorov scale, maybe you don't need to resolve that Kolmogorov scale in some of the DNS simulations. Now, I would agree that you don't need to resolve the flame structure down to the Kolmogorov scale, but the turbulent structure, the question is, the Kolmogorov scale eddies get rid of the turbulence as just fast enough to offset the creation of turbulence that's created by the large scales. So if you don't resolve the small scales in the Kolmogorov scales, your simulation may be creating more turbulence and not getting rid of it fast enough so that it builds up. Now, I don't know if that's true, but there is some discussion about that you may even need to put some artificial destruction of the turbulence to simulate what the smaller scales do. I mean, but that'd be on like an LES submodel. But we do know that if you don't simulate the destruction of the turbulence and it starts building up, then you get totally unrealistic answers. Fortunately, it's all at the Kolmogorov scale. Other questions? Yeah.
So, stability.
Mm-hmm. 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 Yes. The question is there some way to understand and include the hydrodynamic instability, which is Landau's idea that I showed, that flames would just naturally, inherently wrinkle independent of turbulence. And Professor Ken Bray wrote a paper a long time ago about the 22nd symposium, which he did his sort of K epsilon model, and then he put a term in. He came up with a term in the the K epsilon equations that attempted to account for hydrodynamic instability. Now, nobody else, I don't know if I may be the only person who read that paper. Nobody else seems to use it. It was a very nice paper, but I think most people just ignore that issue. They just want to say turbulence causes a wrinkling of flames, turbulence causes mixing. But it's difficult to include hydrodynamic instability in a model, because the models are all time averaged terms, and the hydrodynamic instability is a complicated, unsteady process. But if you were interested in that, I would suggest you look at KNC Bray. If you just go to Web of Science and look at all his papers, there's one paper, maybe he's got more, but on hydrodynamic instability terms added to models. And if you can find it, if you can improve it, it would be great. No, the question now is if you have an experiment, can you determine how much of the wrinkling is due to the inherent hydrodynamic instability that the flame likes to wrinkle, and how much of it is due to the turbulence? And I don't think there's a good way to do that. What Adam Steinberg showed was that if you look at individual eddies going through flames, you can sort of separate the initial wrinkling and then the later wrinkling, but the hydrodynamic instability is there all the time. And his thesis work suggested that flames start to wrinkle due to eddies, and then later on they're on their own, and then even when there's no eddy around, they'll just keep wrinkling and wrinkling. And so it really should be modeled. The question is, well, does it need to be, or what fidelity do you want? And maybe the answer is the DNS is the ultimate solution, because if it's so complicated that it's hard to model, maybe we should just forget about it in the models and look at it in the DNS. Again, a model is not attempting to get everything right necessarily. It's attempting to get enough right that you can build a jet engine. Okay. Let me go through a few more slides, and then we'll take another break. I mentioned these papers. I put them in my handout material. If you're going to look at how well measurements and models compare to each other, I think the best place to start is with the TNF work, and then go on. And the next topic that I wanted to talk about was modeling premixed turbulent flames. And this is the Bray flame surface density model. And it's quite a different concept than what I talked about before. Just to give you some background, I sketched this. So we have reactants, and then we have some products that are kind of gray here. And the C is the reactiveness, which is the non-dimensional temperature. When C is 1, we have adiabatic flame temperature. When C is 0, we have room temperature reactants coming in. And Professor Bray, a long time ago, realized that the PDF of this reactiveness is going to be bimodal. So in other words, it's either going to be 1 or 0, except when this thin line is present at a point, and it's not too often. So this is the gas temperature as a function of time, and it's just either up here or down here. On the other hand, the mean temperature, and I should have put a bar over that. That should have a bar over the top. The mean temperature now would be, if you were to now take this ensemble average and use, now let's see, this is in X. So if I converted this to time, and then I took the average, then I'd get the C bar, and it would go up as we go in the X direction. The mean temperature would go up as you go through the flame brush. But the mean temperature just tells you the probability that either reactants or products are present. So if the mean temperature is halfway between 0 and 1, that means 50% of the time it's reactants and 50% products. And then the flame surface density is what we discussed earlier. It's the probability the flamelet is in the little box that you're drawing at a given point. And there'll be a higher probability of seeing flamelets here than over here or over here. And so this flame surface density probability is a curve like this. Now, before I go into the details of this model, let's convince ourselves it's worth talking about. It is, in my opinion, one of the better models for premixed turbulent flames. Start by Professor Bray, who's the leader in this field, but now it's been developed by other people. Matthias Imme, and he and I have had some joint students work for us. This is one that he and a student worked on at Stanford, and this is a swirling gas turbine type flame, but it's premixed. And it's one of the DLR canonical flames that they're studying in Stuttgart. And he modeled it. And again, the carbon monoxide is the metric that he used to sort of assess whether his models were working right. And he had several different modeling approaches, but whatever the red one was, which was this part of this method, it gave pretty good agreement with carbon monoxide. Christer Fjörby from Sweden does very nice work, and he compares different models. He's one of the few people who, I guess, has the courage to run lots of different models and compare them. And that's because he doesn't really develop any models, he just runs the models. So he's a totally unbiased person. But he doesn't run every model, so he can't assess all of them. But he's, if you look at this paper, he's done some really good work. And then this paper by Denis Venant, and he's a person that Professor Kandel has mentored, and he's done a beautiful simulations of premixed turbulent flames. This is a stratified burner that Simone Hakrub developed. She's at Cambridge, and she's putting different equivalence ratios in each of these tubes. So it's stratified in a very well-defined manner, and she's done the experiments, and the French have modeled it. And the word that they seem to be calling is a filtered tabulated chemistry, LES. I said flame, it should be filtered tabulated. Okay, so it all is based on the reactiveness, and people use different definitions of reactiveness, but Bray started with this one, so it's a good one. It's the temperature of the gas at any point, at any instant of time, and TR is the 300 Kelvin reactant temperature, and TP would be like 2000 Kelvin product temperature. And if you solve this now for density, and you assume pressure is constant, so you just replace temperature, this temperature here with density, you get this. And tau now is this constant. And so this is our first state relation for premixed flames. It says that if you know C at any point, you can immediately determine the density by just plugging it into this equation. Okay, so that's a state relation. And if you wanted to know the mean density at a point, you could plug it into this equation, where rho of C, again, is this state relation I just showed you. It's simple to derive. You plug that in, but now you have to know the PDF of C dC, and it depends only on C bar and the variance. And so we're saying that the PDF is a bimodal function. Now, even though it's bimodal, this is 0 and this is 1. The two peaks don't have the same height. They're both delta functions, actually. And the area under this is some number, and the area under this is some number, and the two numbers have to add up to 1. Okay. So it's a very different PDF than in the non-premix case, but it just depends on two numbers, and I can plug this in, I get the mean density, which would be, you know, sort of an indicator of what fraction of time am I high density and what fraction is low density. So this is the same idea as before. You have to solve equations for these two numbers at each point, plug them in here, and you get properties which then can go into the conservation equations. So you don't have to have an equation for rho bar. All you need is equation for C bar and the variance, and use this, and you can continue. So let's see, it's 4, so maybe we should stop for 15 minutes, and it's getting awfully cold in this room, isn't it? So maybe we should quit a little bit early.